Welcome back. We are diving into 7.2. This is called verifying trigonometric identities. And we like to shorten that to calling them trig proofs. If you've ever heard people talk about proofs in mathematics, you're going to see why this is probably not going to be your favorite topic for many of you. Some of you are going to enjoy the shit out of this, and it's going to be one of your favorite fucking sections ever. Because it's challenging, and yet you know when you got it right. And it's just like solving puzzles. If you like solving puzzles in a mathematical way, this is going to be much more fun than any of the previous sections are. So similar to what we were doing, we're going to start with some weird trig shit and show that it equals some other weird trig shit. That's the basics of what's going on here. Left hand side has weird trig. And the right hand side has weird trig. Sometimes not weird trig, but usually weird trig. And our job is to prove that they are equal. Our job is to prove that they are equal by rewriting at least one of the sides. Sometimes we gotta work with both, but usually working with one side alone works. At least one of the sides in terms of the other. So that it looks identical to the other side. For this lecture, I'm gonna, and probably future ones, I'm gonna call left-hand side LHS. And right-hand side RHS, because you're gonna get tired of rewriting the same thing down repeatedly, that's not changing. And it's important to like explain why we're doing this. This is vital in calculus to simplifying stuff before we do calculus steps. And I'm gonna like bring up the one we just did. We just had 1 plus tangent squared theta over 1 minus secant squared theta. We ended up getting to -1 over sine squared theta. This is easier to deal with. Easier to deal with this side. Fuck doing this in calculus. That's the point of what we're doing. So when you're going through it, you're gonna go like, I hate it. Some of you are gonna go like, this sucks. Know that I'm trying to teach you a skill that's gonna make it easier for the future. So it's important to have like memorize the identities that we just covered. Including alternate forms. You should have all the reciprocal formulas memorized, the quotient formulas, the Pythagorean identities memorized. Alternate forms is saying something like this, we had sine squared theta plus cosine squared theta equals 1. But get comfortable with cosine squared theta is 1 minus sine squared theta. Things like that, that's an alternate form.
We find out, if the sides are not equal. Or is there?
If I tell you that if you're told that they're equal and your job is to prove it, there's no way that they're not equal.
Not like true false, or like, oh, this is actually false, or something.
Not that I can think of, that doesn't seem like any fun. Or useful. Now, having said that, on the test, some of you are gonna try to force this when you get to this type of problem. Your work matters here, cause if you skip steps and cause you know they're supposed to equal at the end. If you do some like step A, B, and then all of a sudden step fucking G is, oh, look, they match and you don't have the fucking steps in between. You didn't fucking do it, you just jumped to the conclusion that you knew had to be true and you're not gonna get credit. Keep that in mind. So memorize the stuff. And generally the best, let me draw a line between this stuff for it. Try to simplify the more complicated side. Because it's harder to go from simple to complex. And it's easy, it really is, you're gonna like, you'll see. Right here. If I start, this is the simpler side, -1 over sine squared. Do you even know where to start to get to going to that side? I have no fucking idea. Like the things we did, remember this top was cosine squared theta plus sine squared theta. This bottom was cosine squared theta minus 1. You're not gonna jump to doing that. You're not fucking gonna come up with that ever to get to the left side. So if you start on the left side, we have things that will simplify to the right side. And you will fucking kill yourself and hate this course if you try to do the simple side. Sometimes. Shifting everything to sine and cosine is the best choice. Is the best attack sequence. If you can factor stuff. It usually turns out helpful. So let's list some things that, some common things that you may not, or that you've seen but may not remember. If you have like x squared plus 2xy plus y squared, this is x plus y squared. If you have the same thing with a minus 2xy, this is x minus y squared. Then you have your one where we have nothing in the middle, just x squared minus y squared. And that's your x minus y times x plus y. That's your difference of squares formula. And the following two look similar to each other when you're writing them out. X cubed minus y cubed and x cubed plus y cubed. They both start with x and y in parentheses using the same sign that's already present. And then they both have an x squared, xy plus y squared. X squared, xy plus y squared. Maybe I'll do these in red. These signs match what you started with. These signs are the opposite of what you started with. Those are called the difference of cubes and sum of cubes. For example, if we had sine squared x plus 2 sine x plus 1. This is sine x plus 1 squared. I'll call that 4A. 4B is doing other algebraic stuff. Like cleaning up fractions. Or like combining fractions. One over sine theta plus 1 over cosine theta. Gonna be harder to work with than if you get a common denominator. Multiply this one by cosine over cosine. And this one by sine theta over sine theta. And you get cosine theta plus sine theta over cosine theta sine theta.
Never, it's always sine squared, not never sine of x squared. It's not, there's not a thing about this.
So sine squared x is the same as sine x squared. But the problem is, a lot of people are lazy fucks and don't use the parentheses. And it is not sine x squared like that. Because that looks like x squared is in the argument or is the angle. And the angle is not getting squared.
So
Notice that all that's missing between these two is the parentheses, but this one is easily misread.
all of this now is the same as if sine or cosine or cosine or whatever is our x in a sense.
I don't wanna say it's x.
We looked at, well, I mean, the form of this stuff here.
Oh, yeah. Yeah.
It's this,
Yeah,
that's how the form. But like it did.
yeah, we can substitute and stuff in for x and y, but like
It's the same.
this one right here. Is that thing up there, where x is sine x and y equals 1.
Yeah.
That's what you're going with, yeah, that's true. Something else to do. When selecting substitutions. Keep in mind the sign. That isn't changing. Because it's your target. And it's something that may not be intuitive, but hopefully you'll see. If something has. Like a 1 plus sin x. Multiplying. Top and bottom. By 1 minus sin x. That becomes 1 minus sine squared x. And we can substitute that for a cosine squared x. So you can get rid of a plus or minus sign in there by doing some trig operations, things like that. And this works on like 1 plus sine x. 1 minus sine x. You can do it with 1 plus cosine x. 1 minus cosine x. These kind of identities work pretty well. It's important to know. I'll do this on next page. In fact, let me pause, make sure everyone's writing down. This was one of my favorite sections of this class. I remember having so much fun as a stretch, but satisfaction and like pride after a well done problem, figuring out a hard one. That's a nice rewarding feeling and keeps you going. Now that when I got to the test, it stressed me a little bit, like, is it gonna be one I can figure out? Cause if you don't figure it out, you don't figure it out. But. With good practice, you'll get there.
And this, a lot of this is not.
Yeah, this is in 7.2. It's on the list of shit to do. This next one is one of the most important things, and you're not gonna like it. You're not gonna like it the least. We are not solving equations. All the stuff you've done in algebra to solve an equation doesn't apply. Don't do shit to both sides. And the reason why. In calculus, you won't have the other side. So this shit doesn't work. So, I'm sorry, algebraic shit doesn't work. Work on one side only. By manipulating it. No clearing fractions by multiplying both sides. No clearing fractions, etc. And I don't remember my teacher telling me that when I took this class, and that frustrated me, I didn't understand why. But the reason why is when you get to calculus and you have some complicated thing. You don't know what you're trying to simplify it to, you just know that it's not working in what you're trying to do. And you want something simpler that might work, so you have to tinker with it and see what you can simplify it down to. You don't, the other side is invisible in calculus. So you couldn't do algebra, you can't clear fractions if you don't know what the other side is. That kind of thing. Alright, that's the list of shit we're gonna do, let's talk about some examples. Let's verify the following identity. Secant theta times sine theta plus cosine theta equals tangent theta plus 1. Now, they might have told me it, but it might have went in one ear and out the other. I remember not understanding why I couldn't do the algebra, because it makes some problems so much easier. What side looks more complicated to you guys? Left hand side, right? So we're gonna keep the right hand side the same. And I'm just gonna keep writing right hand side as I do stuff. That's not changing. So I got sine and cosine on some stuff. Maybe switching secant to a sine or cosine would help here. Let's rewrite that as 1 over cosine theta times sine theta plus cosine theta.
Distributed.
Now we can distribute it. So if we distribute it, we have sine theta over cosine theta plus cosine theta over cosine theta equals, every once in a while, write down what the side is rather than saying right hand side or left hand side. Because keep writing it down, it keeps you in mind what your goal is. We're aiming for this. Looks like we're already there. What's sine over cosine? Tangent. Cosine theta over cosine theta is 1. And now we have equaled the right hand side. Verified. Many times you can get away with just working one side the whole way. Sometimes you'll work one side down far enough. And it's not gonna be for a couple of examples now. But you work down one side far enough and you're like, the other side's fucking complex too. Work that side down separately, but never like do clear fractions or things to both sides. Unless they happen to apply to both sides. What about? Cotangent squared x times tangent squared x plus 1 equals cosecant squared x. There's a couple ways we can go. So I'm gonna let you guys pick. What do you think is a good strategy here? Which is the more complicated side? The left, so we wanna manipulate the left. What kind of manipulation can we do on the left?
Tangent into one over tangent.
Let's do that. I didn't even think of that one. Let's see how that works out. Equals cosecant squared x. Now we can distribute it. Right? If we distribute, we've got 1 plus 1 over tangent squared x. Equals cosecant squared x. We're actually almost there. What's another way of writing this one? Yeah, switch that one back to cotangent squared x. And we're there, this is an identity. This is cosecant squared x, it's one of the Pythagorean identities. Done. I wanna do that one a couple ways, cause not everyone's gonna think of doing that approach. So let's look at doing that again with something different. You might be inclined, many people will be inclined to, let's just go to cosines and sines. If we go to cosines and sines, this is cosine squared x over sine squared x times sine squared x over cosine squared x plus 1. When you distribute, this becomes 1 plus cosine squared x over sine squared x equals right hand side. Now you could switch that to cotangent, or we could get a common denominator, multiply the first one by sine squared x over sine squared x. And we get that. But the top is 1. And that's an identity. So cosecant squared x equals cosecant squared x, done. And then we'll do it a third way. Not everyone's gonna have multiple paths, but sometimes there's multiple paths to victory. Like Settlers of Catan. There's more than one way to win that game. If you've ever played Settlers of Catan. You can go for the biggest army, you can go for the longest road. Build up your fucking shit. Be a resource king. So, third way for that one. And I know this takes time from other problems, but I think it's worth seeing. That there's more than one way to skin a cat, as my mom would like to say. I hope no one has lost a cat recently. I've said that before and student bust out crying, I felt bad. But. My mama. Just got phrases in me and they get in, they can't, they gotta get out. So we're again gonna keep the right hand side the same. But there is an identity for tangent squared x plus 1. That is secant squared x. And now I would switch to sines and cosines. And what happens here? The cosines cancel, right? We're left with 1 over sine squared x equals cosecant squared x. And so cosecant squared x equals cosecant squared x. And we made the left hand side look like the right hand side and we're done. There might even be other ways. I'm sure there is. I had 2 in my head and. Then Lydia came along and said, let's do something different. And I'm like, oh, yeah, that should work. Alright. Let's change up, go to a different type of example, tangent squared t over secant squared t. Equals 1 plus cosine t. Times 1 minus cosine t. What side do you guys wanna work with?
The right hand side is more common.
Alright, let's work with that one. What is something we could do with that right hand side? I'm gonna write left hand side for now, cause I don't wanna keep rewriting tangent squared over secant squared.
Like multiplying.
We multiply them, this is the formula for the difference of squares. This turns into 1 minus cosine squared t. What can I do with that?
Cosine into 1 over secant. 1 over cosine.
This is sine squared t. What did you wanna do later?
No,
It might work, I'm just like,
no, it's like turn the cosine into 1 over. You can't. The cosine's good. 1 over secant.
might work,
It's a-
well, we'll see, we'll take that path in a second. Okay, so we've got sine squared t. What would make this, now we're looking at where we're going. I need to get tangent squared is gonna be like sine squared over cosine squared, right? So I need to somehow get a cosine squared in here. So if I multiply this by cosine squared t. I have to do it on top and bottom. And I'm gonna write that as sine squared t over 1. And what I'll do is I will switch around where things are located. I will have the sine squared t there, I'll move that cosine squared t on the denominator here to the left one. And I'll move the 1 over here. And have the cosine squared t there. Left hand side equals, this is tangent squared t. Times cosine squared t. And we're almost there. What is cosine squared? Remember, we're aiming for secant. Well, cosine t is 1 over secant t. So this side just becomes tangent squared t times 1 over secant squared t. And we put them together and we get tangent squared t over secant squared t. Which was the left-hand side we were looking for. There. So Lydia had wanted to do this. She had wanted to write this as 1 minus 1 over secant squared t, right? Well, let's see if that works. If we do that, maybe getting a common denominator here would help. And we'll put that together as 1 fraction. And this is still equal to the left-hand side. Now, does that top thing equal anything? Let's see. If we had sine squared theta plus cosine squared theta equals 1. And we divided by cosine. We get tangent squared theta plus 1 equals secant squared theta. So if I subtract 1 from both sides, I get tangent squared theta equals secant squared theta minus 1. And that's what we had here. Other than I use theta rather than t. So we make that substitution there, and that is tangent squared t over secant squared t. And that equals the left-hand side. So that would have worked. Sometimes this shit don't work, but if it's your idea, go with it until it does. Or until you can't figure out what else to do. All right, let's do one where we're working on both sides. Maybe I'll draw a little line there showing that we're doing a different approach. For those that are just looking at the paper later on. All right, let's try, you're gonna love this shit. Cotangent alpha minus cosecant alpha. Over cotangent alpha plus cosecant alpha. Y alpha, just because I'm difficult. Equals 1 minus 2 cosine alpha. Plus cosine squared alpha. all over negative sine squared alpha. So this one, both sides are kind of difficult, right? Maybe we can work both sides at the same time. But each of them doing their own thing. What could we do on the left? Who likes working with cotangent, cosecant? This looks like a pain in the ass. Maybe let's switch these to cosines and sines. So this would be cosine alpha over sine alpha minus 1 over sine alpha. And I wasn't using parentheses up there, so I'm gonna go back and backfill them in. And that was the numerator. The denominator looks like the same thing, but with a plus sign between them. What can I do on the left side? Or the right side? The top part's got a square and a single thing, we might be able to factor it. And it turns out you can factor it. We can write this as 1 minus cosine alpha squared. Or we can use cosine alpha minus 1 squared. You'll see that both of those multiply out to be true. The only difference here is multiplying this by -1 squared, which is 1, would get you that version. And so that one might be easier to work with. Sine squared, what can we do with that? Or do we even want to do anything with that? So if we do something with that, let's see. Do a little sidebar here. We have cosines, I'm gonna just do s squared plus c squared equals 1, representing sine and cosine. If I subtract 1 from both sides and subtract s squared from both sides, I get that. Which means I can rewrite this bottom, negative sine squared is cosine squared alpha minus 1. What can we do on the left now? Now let's go down another step. What's the next thing we wanna do? How do you guys feel about complex fractions? You like them? I don't like them. It looks like we've got sine alpha in the denominator everywhere. Why don't we multiply this side by sine alpha over sine alpha? And remember to put that shit in parentheses so that when you distribute, you're gonna get cosine alpha minus 1 over cosine alpha plus 1. And then I got my equal sign. Now, the right hand side, we've got a cosine alpha minus 1 squared. We have a cosine alpha minus 1. Right now, it's just times another cosine alpha minus 1. That's the square thing, so hopefully, whatever we do with this thing on the bottom will cancel one of these out. And this ends up being the difference of squares. That's like a squared minus b squared. That bottom is cosine alpha minus 1 times cosine alpha plus 1. And now we don't need to work with both sides anymore. The left-hand side is actually where the right-hand side is gonna end up. We cross off, now these two are multiplied together, so we can cross off one set of those. And we're left with cosine alpha minus 1 over cosine alpha plus 1. And we got the same thing on both sides. So this was working both sides. We got through that, so I actually have time for one more. I'm gonna go back to one that I skipped, just to make sure I got to a both sides problem. Let's take a look at secant x plus tangent x over sine x. And we want to make this look like cosecant x over secant x minus tangent x. So if I just worked one side here, let's work on the left. This would be 1 over cosine x plus sine x over cosine x over sine x. So I can make that one fraction on top. Get a common denominator there, we got it already. And we said when we see a 1 plus sine x, a good strategy is to do 1 minus sine x. But if I do it on top, I need to do it on bottom. So this becomes 1 minus sine squared x over cosine x all over sine x times 1 minus sine x. And that top part is cosine squared x. So I've got cosine squared x over cosine x all over sine x times 1 minus sine x. And we can get this down to a single fraction now. Cosine x over sine x times 1 minus sine x.
Yeah.
Well, if I move this sign up, I'm aiming for this. If I move this sign up to the top. It becomes cosecant x. So moving the sine x is this, 1 over sine x is cosecant x. And I can move the cosecant x down to the bottom as secant x. And we're getting close. If we distribute that bottom. I have secant x. Times the 1 is just secant x. And then minus secant x. And I'm gonna write secant x as cosine x here. Times sine x. That's just distributing the secant x on bottom. And we can see that will get us tangent x there. Now, in all reality, I probably, if I were just looking at and starting from the beginning, I would. Try to manipulate both sides, but I think sometimes working one side all the way through gives you more practice for what's useful later on. Cause this equaled the right hand side. And that's it for the lecture. When you're done writing it, you're free to go.